In the realm of quantum mechanics, everything boils down to probabilities. When we measure a quantum system, like an electron's spin or a photon's polarization, the outcome isn't deterministic, it's probabilistic. But what if there's more to the story? What if underlying this apparent randomness are hidden variables that we simply can't see or measure? They propose that the randomness we observe in quantum mechanics is due to our ignorance of these hidden variables. If we knew them, we could predict outcomes with certainty. One of the earliest and most famous hidden variable theories is the de Broglie-Bohm theory. This theory introduces the idea of a pilot wave that guides particles deterministically. According to this view, particles have definite positions and velocities at all times, even if we can't measure them precisely. This contrasts sharply with the traditional Copenhagen interpretation, which embraces indeterminacy and probability. Now, let's rewind to 1935. Albert Einstein, Boris Podolsky, and Nathan Rosen published the famous EPR paper. They suggested that quantum mechanics might be incomplete and that there could be hidden variables explaining quantum entanglement. They argued that if quantum mechanics were complete, it would imply spooky action at a distance, something Einstein found deeply unsettling. Fast forward to 1964. Physicist John Stuart Bell introduced Bell's theorem. Bell showed that if local hidden variables existed, the correlations between entangled particles would have to obey certain constraints. This suggests that local hidden variable theories can't explain the observed phenomena. But hold on, does this rule out all hidden variable theories? Not quite. Bell's theorem doesn't eliminate non-local hidden variable theories or superdeterminism. These theories propose that particles might be connected in ways we don't yet understand, or that the universe is so intricately predetermined that every measurement outcome is locked in from the start. In June 1926, Max Born published a groundbreaking paper. He was the first to clearly articulate the probabilistic interpretation of the quantum wave function, a concept introduced by Erwin Schrödinger earlier that year. He pondered whether we should hope to discover inner properties of atoms that dictate outcomes, or if we should accept that such properties simply don't exist. Born himself leaned towards abandoning determinism in the atomic world, acknowledging that this was more a philosophical dilemma than one purely based on physical arguments. However, not everyone was convinced. Schrödinger, who had initially tried to interpret the wave function in real physical terms, criticized Born's probabilistic view. But it was Albert Einstein's response that became one of the most famous rejections of quantum mechanics as we know it. Einstein respected the contributions of quantum mechanics, but felt it lacked a deeper truth. He famously remarked, "Quantum mechanics is very worthy of respect, but an inner voice tells me this is not the genuine article after all. The theory delivers much, but it hardly brings us closer to the old one's secret. In any event, I am convinced that he is not playing dice." This iconic statement encapsulated Einstein's discomfort with the inherent randomness proposed by quantum mechanics. Niels Bohr, a staunch defender of the Copenhagen interpretation, reportedly retorted to Einstein's skepticism with a memorable quip, "Stop telling God what to do." Following Einstein's famous declaration that God does not play dice, he embarked on a quest to find a deterministic alternative to quantum mechanics. On May 5, 1927, Einstein presented a paper at the Academy of Sciences in Berlin titled, "Does Schrödinger's wave mechanics determine the motion of a system completely or only in the statistical sense?" Einstein may have realized that his use of Schrödinger's field to guide localized particles inadvertently allowed for the very non-local influences he aimed to avoid. Later that year, at the 5th Solvay Congress in Belgium, a gathering of the world's leading theoretical physicists, Louis de Broglie presented his own version of a deterministic hidden variable theory. Unaware of Einstein's earlier attempt, de Broglie introduced the concept of a pilot wave guiding each particle's trajectory through space. However, de Broglie's theory faced significant criticism, particularly from Wolfgang Pauli. Pauli's pointed questions and de Broglie's inability to adequately respond led to the abandonment of the theory shortly thereafter. These early attempts at formulating hidden variable theories highlight the intense intellectual struggle to reconcile quantum mechanics with determinism. Also at the Fifth Solvay Congress, Max Born and Werner Heisenberg made a presentation summarizing the recent tremendous theoretical development of quantum mechanics. At the conclusion of the presentation, they declared, "While we consider a quantum mechanical treatment of the electromagnetic field as not yet finished, we consider quantum mechanics to be a closed theory, whose fundamental physical and mathematical assumptions are no longer susceptible of any modification. On the question of the validity of the law of causality, we have this opinion. As long as one takes into account only experiments that lie in the domain of our currently acquired physical and quantum mechanical experience, the assumption of indeterminism in principle, here taken as fundamental, agrees with experience." Although there is no record of Einstein responding to Born and Heisenberg during the technical sessions of the Fifth Solvay Congress, he did challenge the completeness of quantum mechanics at various times. In his tribute article for Born's retirement, he discussed the quantum representation of a macroscopic ball bouncing elastically between rigid barriers. He argued that such a quantum representation does not represent a specific ball, but a time ensemble of systems. As such, the representation is correct but incomplete because it does not represent the real individual macroscopic case. Einstein considered quantum mechanics incomplete because the state function in general does not even describe the individual event/system. This critique set the stage for a series of profound debates between Einstein and Niels Bohr, who staunchly defended the Copenhagen interpretation. As the debates between Einstein and Bohr echoed through the halls of scientific inquiry, the quest to uncover the true nature of quantum mechanics continued. In 1964, a pivotal moment arrived with John Stuart Bell's groundbreaking work. Bell's theorem introduced a new way to test the validity of local hidden variable theories, proposing experiments involving quantum entanglement that could either uphold or challenge these theories. Bell's theorem posited that if local hidden variables existed, the results of certain experiments would conform to a specific set of statistical correlations known as Bell inequalities. However, if these inequalities were violated, it would suggest that local hidden variables could not fully explain quantum phenomena. Physicists such as Alain Aspect and Paul Kwiat took on the challenge, conducting experiments that tested these inequalities with remarkable precision. Their findings showed violations of Bell inequalities by up to 242 standard deviations, effectively ruling out local hidden variable theories. This was a monumental step forward, but it did not close the book on the hidden variable debate entirely. Another significant no-go theorem, the Cauchy-Specker theorem, further reinforced the limitations of hidden variable theories. Despite these advancements, some physicists, like Gerard 't Hooft, have raised questions about the validity of Bell's theorem, citing the superdeterminism loophole. Hooft has even proposed ideas for constructing local deterministic models that could, in theory, bypass Bell's constraints. In 1952, David Bohm proposed a hidden variable theory that would rekindle interest in the quest for a deeper understanding of quantum mechanics. Bohm unknowingly rediscovered and extended the idea initially proposed by Louis de Broglie's pilot wave theory in 1927, which had been abandoned. Hence, this theory is commonly referred to as the de Broglie-Bohm theory. Assuming the validity of Bell's theorem, any deterministic hidden variable theory consistent with quantum mechanics would have to be non-local. This means that it would involve instantaneous or faster-than-light correlations between physically separated entities. Bohm's theory posits the existence of both the quantum particle, such as an electron, and a hidden guiding wave that governs its motion. In this theory, electrons are unequivocally particles. When a double-slit experiment is performed, the electron passes through one of the slits. and this choice is not random, but governed by the hidden pilot wave. This results in the observed wave pattern. In Bohm's interpretation, the non-local quantum potential constitutes an implicate or hidden order that organizes a particle. This implicate order may itself be the result of a further implicate order, a superimplicate order that organizes a field. Today, Bohm's theory is considered one of many interpretations of quantum mechanics. Some regard it as the simplest theory to explain quantum phenomena. However, it remains a hidden variable theory and is necessarily so. The major reference for Bohm's theory today is his book co-authored with Basil Hiley, published posthumously. Despite its elegance, Bohm's theory has faced criticism. Notable physicists, including Einstein, Pauli, and Heisenberg, felt it appeared contrived. Bohm himself acknowledged this, considering his original formulation of the theory to be unacceptable as a physical theory due to the guiding wave's existence in an abstract multi-dimensional configuration space rather than in three-dimensional space. As we conclude our journey into the enigmatic world of hidden variable theories, we must ask ourselves, what does the future hold for this controversial idea? While Bohm's theory has rekindled interest and provided a compelling alternative to the Copenhagen interpretation, the quest for a deterministic understanding of quantum mechanics is far from over. Recent advancements in quantum computing and experimental physics have opened new avenues for testing the principles of hidden variable theories. Researchers are now exploring the potential of quantum entanglement and non-locality in ways that were unimaginable just a few decades ago. Cutting-edge experiments are being designed to probe the very fabric of reality, searching for evidence that might either support or refute the existence of hidden variables. Moreover, the philosophical implications of hidden variable theories continue to captivate scientists and thinkers alike. The idea that there may be an underlying order, an implicate order as Bohm suggested, challenges our very perception of reality and our place within it. It raises profound questions about determinism, free will, and the nature of the universe itself.